Here's news of an unusual Optica Online Industry meeting this month. On September 24th, we have an exciting opportunity to delve into one of the most promising frontiers of energy innovation: nuclear fusion. I think it's a fascinating discussion you won't want to miss. Maybe you remember back in December 2022, a press conference from physicists at the National Ignition Facility, part of the US Lawrence Livermore National Laboratory. They announced a significant breakthrough in the race to achieve nuclear fusion. Since then, the question has been, how close are we to seeing this clean, limitless energy source power our homes and industries? And what role can modern laser technology play in accelerating this journey? In our previous Optica interview with Michael Campbell, a pioneer in laser fusion technology, we explored the immense potential of lasers in driving this process.
John Kennedy once said, "On Earth, God's work must truly be our own." Fusion is how nature makes energy. And make it here on Earth is a daunting challenge, but it's one that will be forever remembered and make the planet a better place. So my hope is that, answer your question, I think the science will continue to advance over this decade. The 20s, we'll see science continue to advance, and the science will begin to show the promise is close. And then once as that happens, as we begin to see investment by the private sector and the government together, engineers will begin to put together fusion plants. I hope we can see a pilot plant in the next decade.
Wow.
And it will begin. It won't be one that will be the ultimate pilot plant, but it will show that all the parts play together.
Now it's time to discover what the industry is doing to turn these scientific advances into real-world solutions. Join us on September 24th, 2024, from 10 a.m. to 11:30 a.m. Eastern Time. We are bringing together some of the brightest minds in this field, including Carlo Hawley, Paul Rudy, Connor Galloway, Allen Wicks, Zanin Zulich, Bjorn Manuel Hegelik, Andrea Bertoncini, Felicien Legrand, and Joan Briol. These experts will help us lead the discussion, but we want to hear your views on whether laser-based nuclear fusion could be the game changer that replaces fossil fuels, and what the photonics industry needs to do to make this a reality. Don't miss this opportunity to be part of the discussion that could shape the future of energy. So thank you very much. We work very hard on this topic, and I can tell you, we are live worldwide. We have attendees from every part of the world now. This is our number 20-something online industry meeting, and never before I have received so many requests of people saying, I cannot be there, please show me the video afterwards, I want to see the slides, whatever you discuss. There's people who are telling me, please keep my presence today secret. Here we are, ladies and gentlemen, finally, after a long time discussing with all of you individually, welcome to the online industry meeting on laser fusion, on energy. All of us today here are going to discuss how we can work together to advance by a mile one of the most important topics that's going to define the photonics industry on the upcoming decade. My name is Jose Pozo, and I had the pleasure to be leading today a team of people who want to connect you. Our job today, the job of Dr. Helena Diaz, the Director of Laser Technology, Dr. Grace Klonowski, the role of my team is to enable meaningful connections between all of you. And today is all about laser fusion. Many of you are experts already on how the format of these online industry meetings work, but for the new ones, allow me to remind you, we have two sets of companies. We have the integrators. Those are companies who are here to tell us about what they need to make their dreams come true. And from that side, we have Fraunhofer ILT, Blue Laser Fusion, and who doesn't know about LI? Many of you don't know this extreme light infrastructure, right? But the LI systems are here, and they are asking our industry to help them. And for helping, we have the enablers, the Optica corporate members, Highlights, Tau Systems, Nanoscribe, Gentech Electro-Optics, Phasics, Optoman, First Light Imaging. Thank you so much for being here. But those are not the only people at the meeting today. These are the Optica corporate members who registered for the meeting, and they are going to be watching either here at the Zoom room or also in YouTube. We took the time to categorize them in the supply chain. So for those of you watching this meeting, if you want to connect with any company in the supply chain, we will perform the introduction. So you have to do is tell us, I want to connect with Excimer laser here in the photonic energy solutions part. We'll be more than happy to make such introduction because we are all about corporate members. At the end of the day, you notice that you didn't have to pay anything to be at this meeting. And that's okay because we love to provide value to the industry. But this meeting is being made thanks to the support of our almost 600 corporate members who are, with their membership fee, enabling the work that my team and I are doing. So for those of you who are asking, how can we support you? All you have to do is to join as a corporate member, and it's really low cost. For those companies who have revenues of less than 2 million, it's only $800 a year. So please join as a corporate member. We need you to continue doing our job because our job really is to connect companies. We are uniting over 572,000 individuals in 184 countries, and we have the biggest library of market reports, presentations for our corporate members. So you have to do is to join us and you get the access of all the presentations ever given, for example, at any online industry meeting. I also would like to remind you that not only for corporate members, but for everyone, we are live in YouTube. So let me say hello to the YouTubers of the world. Hello, YouTubers. It's great to have you here. If you have any question during the meeting, all you have to do is write in the chat and I will read it in the room. Thank you very much for being with us. And this is, of course, also valid for the people with me here in the Zoom room. If you have any question during any of the presentations, write so in the chat or in the Q&A section, and then you will ask the question yourself, because at the end of the day, it really is all about the meaningful connections. And now, I'm connecting to this meeting all the way from beautiful Germany, Frankfurt. It's raining, the weather is fantastic here. But I'm gonna go from Frankfurt to Aachen. And I'm doing that because I want to connect with the first integrator today. I'm going to Fraunhofer ILT, one of the most important R&D laser centers worldwide. And I'm meeting Dr. Carlo Holly, who is telling us what he needs to succeed in one of the most important topics for the all Fraunhofer centers. Carlo, the floor and the attention of everyone goes to Aachen, goes to you.
Thank you so much. Thank you for the kind introduction and for the invitation to this meeting here. So I'm going to report now about our perspective, how we can bring fusion technology from research into industry. Fraunhofer Institute for Laser Technology in Aachen is a premier contact research institute in Europe for laser technology. And our developments range from developing laser sources, optical systems, the laser applications and additive manufacturing, LPBF, LMD, surface structuring, and of course also technologies needed for fusion. Fraunhofer is a pioneer in benefiting the companies. So in Aachen, we have an excellent ecosystem for photonics innovation, and we are bridging the gap between fundamental research and industry for the development of lasers, laser applications. So we have creation and forming of tailored photons on the one side, and we have the applications, laser production technology, measurement technology, microelectronics on the other side. So our mission is to do research and development application orientated. So we're actually bridging this gap between university and industry. Now, one example here is a laser platform that's been developed over more than a decade now in Aachen from my colleague Dieter Hoffmann and his team. And these are airborne or spaceborne lasers for measurement for LIDAR systems. And you can see they go on airplanes or satellites. And we need to do systems engineering here and make really industrial grade laser sources that are turnkey, reliable, and ready to actually do what they are supposed to do. And this is what we are very experienced in. And we actually want to use these competences now to also help the fusion industry and to advance fusion technologies. So now to fusion, we've all recognized, we've all heard that NIF actually demonstrated the fusion process with ICF. The NIF was designed to do fundamental plasma experiments. So it's basically a single shot facility. So what does it take to come from this single shot facility to a fusion power plant? And this is mainly increase the repetition rate. So we need at least 10 hertz repetition rate for the process, which is practically an increase in the average power of 5 orders of magnitude. And this now comes along with a lot of interesting challenges, meaning development of pump diodes, development of optical components, development of target and target production, target injection into the chamber, development of first wall blanket, the tritium fuel process. So there's a lot that needs to be done, and especially needs to be done in close cooperation between research and industry to actually make IFE a reality. So it is very, very crucial to establish a supply chain and a market for fusion technology. So without a market, there won't be a supply chain. There won't be a lack of purpose in which direction the industry needs to develop, needs to make advancements. And just as I said, there are many individual aspects, many individual technologies that needs to come together here. And overall, there's a high demand for scaling and development of the production technology, for instance, to deliver the drive lasers, the diode pumps, the optical components, the targets, and many, many more. And they all need to be ramped up to an industrial grade. The costs need to go down, maintaining or even increasing the performance here. So in Germany, we have a public funding for fusion research now, which amounts to over 1 billion euros within the next 5 years, which offers us a great potential to actually contribute to fusion technology. And with Fraunhofer, we are at the forefront of these developments. Here you can see Konstantin Hefner, who together with an expert group put together a memorandum on IFE. And with this QR code here, you can directly access this memorandum and read it. So what the BMBF, the German Federal Ministry, did is actually setting up this program Fusion 2040, which is right at the point where we work. So it's private-public partnerships. And I think this is exactly what we need. We need this connection between industry and research to push these technologies forward. So now I'm going to give you 2 examples. The first example is diode laser development. So we know that if we want to go to this high repetition rates, we need to have efficient drive lasers. So if we increase the repetition rates to 10 or 20 hertz, we don't want flash lamps to pump these high energy lasers, but we want to do it with diodes. However, just to build one facility would need the global annual production of high power diode lasers. And the costs, if you take them from the current market value, would amount to multi-billions of euros. So that's definitely not a working point. So we need to improve diode laser manufacturing technology while maintaining the performance or even increasing the performance. And you can see here in this diagram, the costs for the diode lasers in dollar per watts actually need to go down more than 2 orders of magnitudes to have a price point which is then economically feasible for running a fusion power plant. Of course, it helps if you improve the performance of the bars. For instance, you can use 500 watts per bar. We want to increase this to above 1 kilowatt, or demonstrations have already shown that it's possible to go to 2 kilowatts per bar. And if you want to read more about this, colleague Konstantin Hefner, me, and experts from industry and research have written this white paper about the perspectives of high power pump diodes. So we are just about to initiate a project, the Helios, with the goal to advance diode pumps for high energy lasers. So the key topics we want to address is develop kilowatt class QCW bars, advancement of scalability and production. So bring in automated production for this pump systems, building up high fill factor stacks, making sure to have the thermal management correct, and delivering the optical output performance that we need. So this again is planned as a private-public partnership program together with leading industrial diode laser manufacturers and research institutions. The second example that I want to show you here is the project Prefusio. In Prefusio, and this is an ongoing project, and you can see the consortium, the project partners here. The project is funded by the Federal Ministry of Education and Research, the BMBF in Germany. And what we want to do is develop components, so optical components and materials, which are actually able to sustain this high loads and energy, and can be used in this with this higher repetition rate for kilojoule beamlines. What we in particular do is we simulate laser concepts and make sure that we have the right requirements for the components that need to be developed. And on the other hand, we do research on laser-based optics manufacturing. So with the laser, you can ablate material from an optical surface and you can actually shape it. You cannot only make a certain flat surface, but you can also put, for instance, like free-form shapes on this and do this all laser-based. So to wrap it up here, Fraunhofer plays a central role in bridging between academia and the laser and optics industry. That's always been our role, and that's also the role that we now want to take for the advancement of fusion technology. We deliver robust and industrial-grade solutions. Overall, the industry needs to work towards a supply chain for a future market. That's the most important point here, to realize an IFE at one point. And the advancements need to be made in scaling of the technologies, lowering the price points, and maintaining or even improving the performance of all these individual components. And this is really then the last sentence. I think fusion is a great chance for photonics research and industry. Thank you so much for the attention.
Thank you very much for a great presentation. We have here a way for us to understand your requirements. And here for us, we have a few people who would like to get in touch with you, but there's a company coming all the way from a city very dear to me. The company is Monochrome and the city Barcelona. Carles Oriach-Font, thank you very much for joining us today. You are one of the key suppliers of laser diodes in Optica, and I guess you have a question for Carlo.
Well, thanks, Jose, for the introduction. Yeah, well, in fact, our main interest, and replying to what Elena posted on the chat, is that we would like to clearly understand what are the requirements for the pump diodes that are needed for nuclear fusion. So you mentioned kilowatt class laser bars. I guess we are talking about 808 nanometers in wavelength, but maybe other wavelengths may be also of interest, depending on the material that you want to pump. Yeah. And also stated 10/10 square centimeters, but what would be the power in that area? Because I guess it's multiple bars, seeing what you presented. So essentially getting to know what are the requirements for these pump models.
Yeah. We love specifications. So the more detailed, Carlo, that you can give us on the specs, the happier we are.
Okay. I mean, we can also talk later about more details on all the specs. So first of all, let me see what the power level. Right now, there are bars out which deliver 500 watts in peak power. So this has already been demonstrated. Also above the 1 kilowatt range is possible. So of course, it would be great to achieve the 2 kilowatts per peak power per bar, but then you probably reduce your lifetime. So this is always the problem, right, that you might run into. With the wavelength, you just said the 808 or 8XX nanometers, and it depends, of course, on the laser medium, and it's not decided yet which laser medium you want to pump. So we're actually aiming to in parallel develop both platforms, the 8XX and the 9XX devices, to at one point make a down selection and be able to deliver the right devices here. Overall, it's a mixture of different requirements, and I think one very aspect point which I mentioned is the price point for the overall package, and this price point really needs to go down, and therefore standardization is a very important topic, which is also happening due to connecting the industry and the manufacturers here, because then you can actually rely on standardized processes, bring them together, and to be really able to have these two orders of magnitudes actually in the dollar per watts.
So very high power, ultra high power, very low power consumption, and if possible, make them very robust, stable, and cheap.
Yeah,
I
and I
think
missed, sorry, I missed one answer here. So you want to aim between 10 to 20 kilowatts per square centimeter, but it depends, of course, on the laser material, because you asked for the intensity in the area that we need to achieve here. Yeah.
we have a lot of questions and comments for you, and I'm going to start because there were a lot of things that we wanted to discuss today. And one of them is actually brought very quickly. I thought it was going to take a bit longer, but brought very quickly by a representative from Optica Corporate member Corning, Anthony Bauco. Thank you very much for joining us today. Anthony with us. Hello,
Can you hear
Anthony.
me now?
Loud and clear.
Okay, yeah. So the question I have, given that you are located in Germany, there's been a lot of change in the government's approach to fission power, and I'm just curious: are you at all concerned about the security of your funding moving forward for these efforts in fusion?
These are two different lanes actually. So a fission is let's say a different funding route than what we do here in fusion. So we are actually not concerned at all.
I think I don't know, but Anthony, do you want to comment? Because I believe there is reason to be concerned, but we will maybe address this when after the LI presentation. But Anthony, do you want to comment further?
No, that's fine. I mean, obviously things will change over time. I guess we'll see what happens.
We're going to come back to this point and after we had the presentation from the LI, because of course we are all excited and of course I a bit concerned about this. There's another comment in the chat coming from one of our enablers today, so I'm going to give him the floor. Coming all the way from Tau Systems, Bjorn Manuel Hegelich. Bjorn, first tell us what's on your mind and then share with us how you could maybe help or partner with Fraunhofer ILT on this topic.
Yeah, well, thank you very much for having me. And thanks for that great introduction there from our colleagues from the Fraunhofer Institute. Especially there was this one slide from one of the Livermore publications that showed that the fusion power plant is much more than just the laser. There's many different challenges, from new material science. The laser has to work at 10 hertz, but so has everything else. So control systems, target injection. Targets need to be mass fabricated at a cheap price and with an energy balance that is ultimately positive, of course, right? We want to make energy. If you take more energy to make your targets than you ultimately get out of them with anything, shipping and all that. So that's a problem. Mass manufacture like this, it's 1 million targets per day per power plant. So we're talking really high volume manufacturing. There's going to be metrology. There is many different challenges for many different industries. And at Tau Systems, we're looking at providing technology solutions to address these sub-challenges, to characterize materials, to metrologize targets, to develop high rep rate, high data flow, control systems, machine learning, this type of thing. And I believe, that's just my personal opinion, this is still going to be a multi-decadal and multidisciplinary effort where many companies will have a role in providing bits and pieces. I'm not so sure if I would say that the first big power plant is built by one company, or maybe more by something like a Manhattan project, but we'll see.
You have one slide to share with us, so please go ahead. And while you share the slide, it's like, could you tell me by when do you think we will have the first laser-enabled power plant?
Let me just make sure I get the slide.
And by the way, I'm asking everyone in the chat to comment. By when do you think we will have the first laser-enabled power plant? And my guess is easy. I'm going to say it easy. I'm going to say I think for me it's 10 years.
Yeah, and I would probably say it's going to be a lot more than 10 years.
Somebody said 100 years. I love I
No,
don't know if
well, not 100 years. I say it's probably going to be more like maybe. I mean, for a power plant, of course, it depends on how you define a power plant. But a power plant on the grid that's actually putting power back into the grid, I'd say at least 20 for that, because there are so many there's so many challenges, right? It's like what you see
Yes.
on the slide is something we'll do at Tau, which is building compact particle accelerators and light sources, especially X-ray sources. And those are very versatile tools, right? Accelerators are some of our most powerful tools. Unfortunately, they're also very, very large, campus size, $1 billion, and we shrink them down. And that means you can now have this as part of your toolbox, basically. You can have one where you need it. You can use this to look at components, at materials, at how materials interact with radiation, because you can create the radiation and use it and diagnose it. And so think about nuclear cross-section measurements, think about radiation testing of materials, wall materials. It can generate neutrons, but also of electronics. How does that work? Think about developing. We heard before from Fraunhofer, there's this effort to develop high damage threshold optics. Well, we're working with laser systems and developing laser systems that will have significantly more rep rate than what's needed for a fusion plant. So 10 hertz for a fusion plant. The system we are just right now putting together in San Diego is going to have 100 hertz. We're looking at going well beyond that. So you can do accelerated testing, accelerated aging, these types of things. And these are all big individual challenges. And then they all have to be brought together. So yeah, I think we're gonna take a little while, and we're going to take it's going to take a village, and actually a very global village, I think, a large community to bring this all together. And if you do, I think we just sort of launched into some of the policy questions there. This is also going to be interesting. A lot of times it's said, okay, with fusion power plants, we can ultimately solve global climate change. Yeah, maybe if everybody has one. But given the current political situation, are we really going to export 10 megajoule and more class lasers to everybody in the world
No.
that also have the ability to pretty much make any isotope you want, because you get neutron fluxes that are beyond anything we can produce today? I mean, this is a very sensitive technology at the end of the day, if you can put it together. And how will that play politically? I mean, one can maybe hope that at some point we'll rally towards solving the larger problems, but today that would be very hard to see. Let me put it that way.
The dual use of optics technologies is actually playing against us in this development, and we are very 100% aware of that. And thank you so much, Bjorn. We have a question this for you and for Carlo together. That question is coming from Daniel Sati from DIY Optics, Do-It-Yourself Optics. Daniel, you have a question about the pump driver electronics.
Yeah. Hello, everyone. Yeah, so basically, just like Björn said, there's a lot of other things which need to follow up the technology. And I think recently I was looking at Jenoptik QCW switches, QCW pumps, which it's really hard to find the driver electronics which really pushes out within a short time. I don't know, hundreds of amps, something like this. Can't exactly remember what was the number, but is the electronics the limitation at the moment, or you really see this as a pump availability limitation? I don't know who can answer the
Well, I mean,
question.
I can give a first whack at that. I think it's not just the electronics. I think there is a lot of advances needed and being worked on. Some of them are the electronics, but a lot of them are also, it's how do you integrate them? I think at the end of the day, one of the biggest challenges is going to be cooling. I mean, you'll be talking about assembling at the end of the day many, many, many megawatts, gigawatts of diodes. I mean, there's a lot of power going in. So cooling, I think, will be one of the major challenges, honestly.
Okay, thank you. All right.
Carlo.
Yeah, it is. So of course the electronics needs to be developed hand in hand, and actually we plan in this project Helios to also do developments on, or our partners do developments on the electronics. I'm not developing electronics here, but from the chip, from the diet perspective, yeah, it's really about the thermal management, and the thermal management starts directly. I mean, it starts in the chip with the efficiency of the chip. Every watt dissipated there will degrade your output performance, will degrade your beam quality, and all the aspects will change your spectrum. And then you need to get it away from the chip as fast as possible, having a certain mechanical thermal management package around it, which should be super cheap, and that's the challenge. That's the challenge actually here, right? To build this, and this is why we're also looking into automatization of this whole assembly.
Carlo, now that you have the word, I would like to ask you, could you specify a bit the optics needed for the ultra high kilowatt power laser that you're actually using?
Mm-hmm. So, I mean, we're looking into larger optics. So it's about let's say it's starting from 40 centimeter by 40 centimeter glass slabs. And one plan to go actually forward is by aperture scaling, right? When you want to increase the average power, you don't want to deposit all this power in the same beam diameter, in the same beam size. So you increase your aperture by more or less maintaining the physical parameters of the amplifier laser. So this is what we're planning to do. And then of course it goes into the details. You don't want to have defects on the surfaces. You want to have coatings which sustain this high energy inputs, and also make sure that you actually have material which can be cooled in a good way, because of course if you make them larger, then you have all your temperature, your heat accumulating in the center of this optics.
In offline discussions over the last months, we have noticed that there is still challenges when it comes to the IBS coatings without defects on these large surfaces. For that, we invited today Optica Corporate member Optoman, Andrius Acho. Thank you very much for being here. Please let us know what you do, and most important, how you can help the companies today in the room.
Yeah, so hi, Jose, and hi, everyone. Thank you for a very nice introduction. And yeah, I think this is a good time for me to introduce you to a superhero. Yeah, and as we all know, and as we heard today, the world is buzzing with excitement about the development of fusion energy and how it will revolutionize our future. And we can all imagine a world where powerful lasers create a clean, sustainable, and virtually limitless source of energy. And it may sound impossible today, and as you guys said it many times, but which is why we might just need a little help from a superhero, don't you think? Yeah, so let me introduce you to Optoman and Optoman's superpowers, you ask? So he manufactures IBS-coated laser optics with an exceptionally high damage threshold built to handle the extreme power levels needed in fusion applications. These optics have an increased lifetime, ensuring durability even under the toughest conditions, which helps reduce the downtime and cost, which is of vital importance here. Plus, the coatings are highly repeatable, offering consistent performance with minimized losses, ensuring every bit of the energy counts. Now, what makes Optoman truly heroic is the scale at which he operates. I'm not sure if you've noticed, but in this picture behind Optoman, you'll see a little fun comparison. Yeah, that's right, a banana for scale. So while a banana might be a snack to us all, here it's helping you visualize just how large our optics can be. This capability is crucial, and it's been mentioned today many times that for future of the fusion energy, large, durable, and precise optics are the backbone of these powerful laser systems. So with Optoman on the job, the dream of clean and sustainable fusion energy is one step closer to reality. Yeah, and remember, your laser is only as strong as its weakest link, but Optiman, and with Optiman, you can be sure that your optics won't be that link. Yeah, so thank you, and yeah, we can continue the discussion about the superhero optics.
Thank you very much. And I later on in the meeting, we're going to ask how your superhero measures the LIDT. There's a few people here who can help you with that. Andrews, thank you very much for this. But now I would like to, with no further ado, give the floor to a company that everybody asked for us to bring today on the floor, all the way from California. Thank you, Hugo, for being with us today. Thank you so much for bringing blue laser fusion to the room. Tell us what is your current state of development, and most important, as usual, how can we help you do things better and faster? The floor and the attention of everyone goes to blue laser fusion. Paul Rudy.
Good morning, good afternoon, everyone. Can you see my slides okay?
Crystal clear.
Great. So happy to be here, and thank you again to Optica for putting this incredible event together. It's super exciting for Blue Laser Fusion to join here. So my background is photonics. I worked in grad school at Rochester, and then went to Silicon Valley and worked at Coherent for many years, where we were actually supplying pump diodes to an early sort of attempt at a diode pump version of NIF. And of course, Coherent was supplying a lot of optics into that world at the time. So familiar with NIF over the years. I joined Shuji Nakamura here to commercialize laser fusion. And it's quite a kind of a unique endeavor. Been involved in the past in sort of classic high-tech startup with successful growth of a gallium nitride laser company over the last decade or two. Fusion is quite unique. Fusion requires collaboration in ways that maybe classic Silicon Valley startups aren't used to. And Shuji, after inventing the LED, immediately turned to fusion after the gallium nitride success story of solving the energy consumption problem related to lighting. So now on the power generation side of things, Shuji's teamed up with Oda-san from Japan, who originally has a plasma physics and nuclear physics background. As you know from the type of team that the company's put together early on, it's extremely cross-disciplinary. And many topics mentioned already in this great discussion so far touch on that. It's an incredible challenge. So it requires a target modeling and fabrication capability and understanding and collaboration. Laser beam combination, in the case of blue laser fusion, coherent beam combination combined with optical enhancement cavity. Quite a unique combination, which I'll talk about some more, brings unique challenges. As we see with most things in high technology, the technology challenges bring opportunities and require here in the fusion space collaboration to solve them. There's of course target injection and reactor design, as mentioned by some of the last speakers. So it also requires building the company for a mindset to collaborate, to accelerate commercialization. This means, of course, government program development, but commercial supply chain partnering. It requires an outlook to cost and design trade-offs for practical commercialization at every turn. And then, of course, on the export control side, but also just regulatory, right? You're getting into a regime that maybe many laser applications aren't used to. It's an international approach that Blue Laser Fusion's taking, with a lot of emphasis in Japan to start, but excited to expand that emphasis into Europe, and of course strongly coupled into North America already. The center picture on the right is Osaka University, where there's strong collaboration with Blue Laser Fusion already running. And I'll talk about that more. Big picture, most people here see the context, but I just wanted to give a little version of it from our view. That's a picture of 3 Mile Island on the far left. I grew up there. I was evacuated in first grade in central Pennsylvania. News from the day before yesterday, I think, on CNN. 3 Mile Island has been mothballed, but it now is coming back with Microsoft needing energy for AI. And they're going to they're attempting and planning, announced to restart fission there. So quite a challenge. Of course, we know about the safety and regulatory perception and issues experienced in the past globally. Magnetic fusion is wonderful and taking quite a while to get ignition. Laser leapfrog that, of course, with NIF, which we all know about, and many of us, that's why we're here today. Laser at NIF, of course, was based on sort of 1980s technology, lamp pumped, so challenged by efficiency, reliability, rep rate, cost structure. It was not designed to be a commercial power plant, of course, so no fault to NIF. It's incredible scientific demonstration, which we all can be proud to stand on the shoulders of moving forward. And we have strong, we actually just had a resident engineer interning at NIF. So really incredible respect to the success there. Our approach at Blue Laser Fusion is quite unique, I think, using coherent beam combined injection laser into an optical enhancement cavity. This gets into the 10 to 15% wall plug efficiency range, 10 megajoule 4 hertz sort of baseline design. It's, of course, meant to be modular, designed for reliability. And the target choice for the actual fuel target is high gain, but designed with intent for cost in the final application. Okay, so cartoon version of sort of what we're up to. A high rep rate coherent beam combined laser starts on the upper left. It's think of it as a megahertz style high rep rate low pulse energy source getting injected into an optical enhancement cavity. This is a phase lock CBC laser. And those optical enhancement cavity approaches more than 10,000, actually heading toward things like 100,000 plus. This requires 5.9 reflectivity optics, but headed toward 6.9 in any way possible. And of course, incredible pulse energies here. The output of the OEC ends up being nominally 10 kilojoule source. And so roughly there's 500 pairs of those to get a 10 megajoule source for fusion. That ends up getting put onto a high gain target. If you don't know about OECs or optical enhancement cavities, that's a picture of LIGO. LIGO routinely does this with CW lasers and lower average powers, of course, and pulse energies. LIGOs around the world, operating today and in Japan, in Europe, as well as across the US. The target I won't get into a lot today, but it is similar to the DT target used at NIF, but has some neutron reduction layers in it to help the cost structure and sort of overall reactor maintenance. It's not a PB11 target, which would require order of magnitude higher in pulse energy from the laser source, which would be problematic. There's talk about market opportunity. I'd point you to, if you haven't seen it, Ignition Research just issued a report a few weeks ago. It's optimistic for sure, but the question of when will there be a first power plant on the grid? Ignition Research is describing 2035, and the 20% adoption by 2050 from their work. And this is caused by an insatiable demand that isn't being met with today's renewables, which of course solar and wind are wonderful, but they're not on demand. They're not sort of plug and play, drop in to the existing sort of brownfield sites of coal plants, natural gas, or say fission plants. This report, is something anyone could access, and it has some interesting assumptions in it. And I think the critical element here is it does represent an enormous opportunity for the photonics industry, from optics, crystals, pump diodes, as mentioned previously. Okay, one of the key things we do is to collaborate cross country. Japan, US, Germany, around the world, in Asia, photonics is so incredibly important. We work specifically initially with Japan, and in a way that we start with our baseline first gen laser and OEC and target. And we're able to use that at Osaka to run shots on prototype targets. And then we, up in parallel, we upgrade the laser, we scale that, we scale the OEC, improve the target, and then inject that over to running shots. Places like NIF or Rochester Omega System are incredible. They're booked. It's extremely difficult to get time. So until we have our own laser reactor facility, we run shots through collaborations. Lots of other collaborations beyond just shots and target and laser, as mentioned over on the right. Okay, the collaboration development goes beyond, say, a university. Of course, government labs, the commercial supply chain is so important. We have strong collaborations, development programs running. The workforce development is critical, right? So in addition to just straight hiring or interning, we're working hard to get the word out to the photonics community and the energy community to develop the workforce, because the outlook here is insufficient as far as hiring needs for the industry. Many fusion companies are collaborating, many fusion companies are hiring. I would venture to say maybe all. It is one other example I didn't mention, but I should have. Caltech and the LIGO collaboration we have running, which is sponsored by the Department of Energy, and a recent Infuse Award, is deeply appreciated. And bringing LIGO type OEC technology to the energy world is quite exciting. So thank you for that. I'll pause for questions.
Thank you so much. It's really nice to see that this industry is creating so many opportunities, and also is getting beyond. It's like the development is finally moving, and we start seeing things. We have a very good question that is coming from Morteza Santana from NSTIR. So Morteza, could you please open the mic and ask yourself your question? Morteza?
Yes, of course. Thank you.
Yeah.
Can you hear me?
Yes.
Yes. As I remember, the most problem in the laser fusion is hit the position in the active media, especially when we would like to use more than 10 hertz repetition rates. I would like to know, it is possible that we use liquid laser instead of solid and other kind of laser?
So I'll just make a quick comment on that, and then certainly invited to any other panel members. There is a program, I believe, if you look into the literature through the HELADS program, some liquid laser type approaches in directed energy, high-powered defense. Now these typically are CW approaches, but certainly could be adapted to the high energy sort of fusion approach. So there absolutely have been activities in the past, and I would say the development of ultra-high average power lasers, typically CW, in the directed energy world for defense applications. Many of those have been dual use along the way, but many of them have been adapted for defense, and maybe elements of those end up being ITAR. Blue laser fusion isn't involved in any of that, but I do know liquid laser technology that is, and it may have dual use for energy, may not. The approach we're taking is coherent combined sources, typically rod-based or even fiber-based. The OEC, because we're effectively pulse stacking, allows us to go from a high rep rate or even CW sort of source over by using a pair of mirrors in a vacuum to a lower rep rate. So think nominally 1 to 10 hertz kind of source with very, very high pulse energy with a pulse stacking of 10,000 to even 100,000. And so that maybe gives the blue laser fusion approach a different acceptance tolerance to injection lasers, which can even be fiber amplifier based. And that for us opens the door to requirements of needing preamps and amps and isolators that are common maybe to the high power fiber laser world. And as well as the coherent beam combined techniques, which have been developed so amazingly over the past 5+ years commercially.
Yeah. So
Thank you.
thank you. So actually, Born, you have a comment on that, please? Go
Yeah,
ahead.
I have a small
Yes.
comment on that. I mean, first I want to say, of course, coherent beam combining is also a technology that's widely used in directed energy and laser weapon systems, especially with fibers. And pretty much anything, it doesn't even matter. I mean, if you look at the ITAR regulations, anything that gets you in the kilowatt average power range will be ITAR controlled in the US. There's really no doubt about that. It's a pity that the colleague from Exheimer couldn't be there, because they work, as far as I understand, on a large gas laser, not liquid, but gas, and a lot of gas optics, which is really cool if you think about it. I was looking forward to hearing more about that, but yeah, maybe some other time.
Take it to you for sure. No worries. We arrange that. We arrange a meeting in between you and Exheimer for sure. Okay, you can count with that. We also have a. Oh, sorry. Yes. Yeah. Okay. So we have another question that is coming straightforward from Luxembourg, from University of Luxembourg. Is Kushaldas Badam. Kushaldas, could you please open your camera and your mic and make your question yourself? Is it Kushaldas?
Hi, audible?
Yeah, I can hear you.
Yeah. Sorry, I cannot turn my camera on. I'm not in really good position.
Okay.
So my
Live.
so Paul actually mentioned 10 megajoules of energy, and the power was the efficiency was 10% for the lasers. I was wondering, the 10 megajoule striking on the target, or is it the input energy of 10 megajoule and then you decrease it to, so basically 10% to 1 joule for striking energy? Is it clear?
Yeah, good question. Yeah, so as you may know, NIF operates in sort of the 2 to 4 megajoule per pulse. We're operating here up toward 10 megajoule per pulse output, and that comes from 500 pairs of OECs. So each source is say 1/1000th of that. But yeah, onto the target is 10 megajoules. That gets you into a gain nominally in the 75 to 100 range, which is at those rep rates what's needed for sort of gigawatt scale power plant designs. Yes.
Yeah.
Thank you.
Thank you. So something somebody that can help actually with this, because I mean we really need to measure what is the energy, and we need to measure the pulses, and there is more about the pulses, about more than the energy. But there is Felician Legrand from Gentech O, who can help with that. So this is our corporate member. So Felician, please, all the floor is yours.
All right, thank you, Elena, for the introduction. Hello, everyone. Quite happy to be here. Very exciting times we're living in. Yeah, so, okay, let me go ahead with this and sharing my slide. It's actually a poster we made for the Equal conference 2 weeks ago. Could you just tell me if this is running? Elena, do you see the poster?
We see it crystal clear. Go ahead.
Sounds good. Thank you, guys. Okay, so yeah, first of all, I'm Félicien Legrand, Phil, here at Gentech EO in Quebec, Canada. I'm a physicist by training and the sales manager for the North America. We cover a global market, and pretty happy to present technology here on this Optica conference. So we provide solutions to measure laser beam performances. I'm talking laser beam power, laser beam energy, and beam profile. It's a very good timing. So yeah, we prepare this poster. Sorry, this is a lot of information packed here, and I'm sure we get a chance to talk about it again. So first of all, the first one I wanted to mention, this is the volume absorber calorimeters that we see on the left side here. They're the ones that they use at NIF to measure the pulse energies of the 192 laser beams before they get combined onto the target. So it relies on large volume absorbers made of glass, diffusing the intense pulse energy, and transfers the energy to thermocouples to measure voltage, a rise in voltage. This is the curve that you see to trace. And the rise in temperature of those thermocouples, it's very, very repeatable. So the pulse energy measurement can be calibrated off NIST standards using this trace, using this response. So we provide tools to get a absolute measurement of pulse energies using NIST standards. And that works very well for single shots, typically at the kilojoule level, nanosecond, or even femtosecond shots. And it's great for use in vacuum. So again, you see the tiny picture, but the poster will be shared to everyone attending a conference. So the tiny picture is the ROVI assembly calorimeters that they call them. This is a bundle of four calorimeters. They go into the beam path to make measurements. Otherwise, it's just removed out of the beam path to let the beam go to the target. Okay, with the repetition rate now, another challenge. For that, we prefer pyroelectric crystals to provide a faster response. And that's the round one that you see in the middle of the poster here. So now they provide a capability to measure pulse-to-pulse energies up to 200 hertz, so perfect for the development of higher rep rates in this field and for fusion. So 200 hertz up to 700 joules per pulse, or 350 watts of average power for the standard product here that I wanted to present, with the 195 millimeter aperture that we released this year. And this technology, the pyroelectric crystals, have been used by all the US, all the LaserNet US members across the US, as well as Eli NP and various commercial laser system manufacturers for integration. And more recently, the various companies working to make inertial confinement fusion a reality. We have many partners in this field, and people trying, integrating, and taking advantage of this technology. Then the third item on the top right, for average power measurements only, those are the water-based calorimeters, up to hundreds of kilowatts. So for manufacturing, directed energy application, as has been mentioned, and as well for average power measurement in watts for this field. And finally, I wanted to present the high energy beam dump technology that we like to call the portable black hole. That's the one you see with a 45-degree angle. This one has been adopted and installed at the Eli NP facility to dump up to 10.2 petawatt in a single shot with less than 0.1% of back reflections. And the device is passively cooled and ready for ultra high vacuum. So unique technology that's really helping systems with a high peak power, high energy to dump safely the energy and or measure it to make sure the laser is performing as expected, the beams are well combined, and to make optical pickups as well for smaller detectors, fast to not block the full laser beam and to run diagnostics in real time. Machine learning has been mentioned. It's just getting stronger and stronger to use the readout of those meters and derive a strategy to make the laser better down the line. So, okay, so that sums up what we can offer for fusion development in a nutshell, for laser beam performance diagnostics, energy measurement, average power measurement, and we do beam profiling too, off the shelf for custom. We've been actively gathering the needs of the community, so please interact. We love to play an important role in this. This is, again, very exciting times, and let's keep in touch. Thank you.
Thank you so much. Thank you so much, Felicien. And actually, I mean, I've been, I mean, for the people to know, yes. So Gentekio is part of several of the projects in nuclear, and they are like very good doing handling very high energies. But someone that is has a very interested contribution into the nuclear energy is Nanoscribe, and we have Andrea Bertoncini. So Andrea, I would like you to introduce what Nanoscribe did for nuclear with the collaboration with the lab. Thank you. Go, Andrea.
Andrea, we can't hear you because you're on mute. That was the sentence of the pandemic. So well forgotten. Yes, please unmute yourself so we can hear you loud and clear.
Yes. Thanks for unmuting me. I didn't find the button. So I was thinking, what breakthroughs could occur if fusion target design were not limited by manufacturing capabilities? So I'm Andrea Bertoncini, a nuclear engineer working at Nanoscribe, a 2-photon lithography micro 3D printing company. And I'm excited to share with you how the recent developments could be applied to advanced nuclear fusion. So Nanoscribe has a proven track record in manufacturing foams for fusion targets within academic research. We can get foams with struts smaller than 1 micron diameter, spanning several millimeters in size. And we can print these complex lattices structures with high precision and a huge range in densities. So what you get is like complex lattice structure with high precision and variable density. So typically fusion targets are composed by 2 parts, right? There is the foam, and then there is a smooth, precise shell, which contains the fuel and act as an ablator. So in the past, we were not able to 3D print the shells because they require optical quality and our process was not good enough. But now with the development of 2-photon grayscale lithography, we are able to also print the shells. So you can see the difference between the old technology and the new technology. And here are the shells. This is an example of a 1 millimeter diameter shell. And please notice the excellent sphericity and smoothness of this shell. So with Nanoscribe Quantum X, you can print from submicron to structures to few millimeter size structure. And you can see in this slide that this is a very huge range. So if you're involved with fusion target design, I invite you to feel free to unleash your creativity and reach out to Nanoscribe to realize your ideas.
And we will use the 2-photon polymerization from Nanoscribe to launch all your ideas. I think you're doing a fantastic job, but I can't wait any longer. When we announced this meeting, we had the pleasure and honor to have one of the initiatives in Europe that has revolutionized the way that we use high-power lasers. It is my honor and pleasure to announce today, in the first ever online industry meeting on laser fusion by Optica, Alan Wicks, all the way from Eli. Alan, thank you very much for being with us. The floor and the attention is yours.
Well, Jose, what an introduction. Thank you so much. And thank you to everyone else. It's great to see some familiar names and faces on there. And I know there's a lot of companies and collaborators with the Eli facilities here that I don't know. I haven't met you, but it's great to have you here. And What I'd like to do is just talk very briefly. We're in a short time window about Eli, what it is for those of you who may not know, but also I think more importantly, what are the opportunities to collaborate together with Eli. So Eli has 3 facilities located in Europe, as Jose said. It's a high energy beam facility in Prague, or just outside of Prague. We have a very short pulse attosecond light pulse source in Eli Alps. And then the nuclear physics facility where we have 2 10 petawatt lasers in Romania. All of these facilities were built at about the same timeline, and I would say coordinated projects, but not really the same projects. So they each were independently built in their countries using European structural funds. And there's a whole history behind lasers, which I'll get onto in just a moment. But just to say that altogether, we have about 800 plus staff at the 3 facilities coming from 40 different countries. So this is really an international organization being hosted by 7 countries, or 3 countries hosting it, but also supported by Italy, Lithuania, Germany, Bulgaria, and of course, Romania and Czech Republic and Hungary are hosting the facilities. We cover a broad range of science. So again, it's not a laser facility per se, in the sense that we don't study lasers. Did I lose my... Can you all see me fine still, the presentation?
Crystal clear. Yes, very well.
We're not studying lasers per se, although we do obviously a lot of laser development, but there's a range of areas of science: radiation physics, particle acceleration. You heard Bjorn speaking earlier about that's a big part of what we do at Eli. Of course, fusion, high energy density physics, plasma. This was really one of the main areas that Eli was imagined, and I'll talk about 2 particular systems that are very unique and specific in this field. We also have a very, I would say, credible computation, simulation, and theory group at Eli, over 50 people working in that field. And then we are also able to do ultra-fast dynamics on the molecular and atomic level, and that also helps us to cover a range of biological and material science applications. So Eli is rather specific in the world right now. I mean, Europe has been very competitive over the last 20 years in installing and, let's say, building high power, high intensity, short pulse systems. Eli is a big part of that. I mean, right now we have commissioning and working 5 petawatt class lasers. So 3 10 petawatt lasers and 2 petawatt lasers that are operating at a relatively high repetition rate. So we have an aspiration to operate those lasers at 10 hertz. Right now, they're operating around 2.5 and 3 hertz. And then there's a whole suite or portfolio of high average power lasers as well. I just circled in the top left-hand corner kind of the systems that if you see kind of the Eli systems relative to other installations in the world, which we didn't put the names there, but just some of you will recognize facilities that you've either worked at or helped develop. But I think the main point is to say that Eli is, for whatever reasons, when the original decision was made to build the facilities, has covered really the broad range from very high peak powers up to very high average powers. And in this particular range is, I think, what's relevant for discussion around the science and the research and the development relative to fusion. But before I get into that, I have to say that Eli is unique in the world. I think there's a few other facilities like the CLF in the UK, facilities around Europe in particular, Dresden, Lully in France. I should mention CLPU in Spain, that are really dedicated user facilities. And what I have here, what you can kind of see in this circle is in the inner circle there, what we call the primary sources, the primary laser systems. So we have 17 primary laser systems. So it's not a single system. And I should also say, for those of you who've not ever been or visited the facility, the systems are designed to work together and to interact. We do that with secondary sources as well. So anything from high harmonic generation to acceleration, as we said earlier. And then all of those different instruments and beamlines can be combined together to create a broad range of diverse configurations. So you can fundamentally come up with, I think, a unique or bespoke kind of experiment. And then our facilities and all these instruments are open to the scientific world, either industry or academia. And many of you have kind of ridden the fence between both or are still. I should say the primary access mode we have at Eli is excellence-based access. So you make a proposal. We have an independent peer review panel that evaluates that. And then if your proposal is accepted and you come do an experiment at Eli, the only thing we ask is that you leave the results of the experiment and the data open. We have a 3-year embargo on the data. And then after that, we're, along with many other European labs, a part of the European Open Science Cloud, and we'll make that data available. And of course, we want you to publish as much as possible in open journals. We have another, I think, very relevant in this conversation mode of access, which is so-called mission-based access. And with mission-based access, a little bit different than just excellence-based. We actually design themes or come up with particular areas of research that we believe are relevant and that Eli particularly can add some value. And this is actually what we call laser-induced fusion or inertial fusion for energy using lasers is exactly the subject that we'll be focusing our first mission-based access program on. It will be also peer-reviewed. The difference here is, I think, longer access times. With the excellence-based access, of course, you have to really kind of focus in on cycling your experiments through in a couple of weeks, and we have to get many researchers in and out. In this case, we will focus on longer campaigns that can build on data over weeks, months, years, and we have to set aside specific beam time for that, focused in these particular areas. Also, a lot of these mission-based access is based around collaborations, bring additional funding with them sometimes, to pay for additional instruments and or modifications to our systems. And then finally, which also I think very interesting, and we have quite a number of partners, industrial partners already, is proprietary access. And there it's paid access as you have at many other labs, at least in Europe, but also in the US. And there the results are retained by the user. We have a data policy and an IPR policy where we're also following very strict non-disclosure agreements, and access to the facilities is limited at the time we have commercial partners. We think we understand well how to work with commercial partners, and or there can be a mix of this. Oftentimes it's a university researcher who's working closely with companies. Right now, if I just look out over the last 2 years when we started our open calls, we have had over 1,000 researchers who've come to Eli already. So actually 1,100. It's interesting, the largest group on the far left in terms of unique researchers that have come to Eli are from the US, so outside of Europe. And then we also have Italy again, United Kingdom, Germany. I think these are countries you would expect given the concentration of the scientific communities there. But as you can see, it's like a long tail distribution, and we have really researchers coming from all over the world to use the facilities. And this is only after 4 calls. I'm happy to say that tomorrow we open the 5th call, and I'll include our contact information at the end of the presentation. But it's very easy to just Google Eli, and you'll be able to access that information as well. I would encourage many of you to do that. In terms of fusion, of course, NIF has, as we said earlier, really been the kind of catalyst for a lot of interest in this area. There was a lot of work done in this area already in Europe. Many of you will know the HEPRA project, which was on the S3 roadmap in Europe back in 2013. It was taken off the roadmap, and that was due, I think, probably to the disappointment at the time, or maybe the unrealistic expectations at the time around NIF. Weren't able to realize some of the scientific goals at that time, but now we have. And since that time, there's been really a great amount of excitement in Europe among the community. People have really woken up to this, very excited. And Eli is very well positioned in this area. Again, not only because of specific instruments, but because it's the largest laser user-based facility in Europe. And it's a very logical stepping stone to do a lot of kind of foundational research. So a lot of the people that are leading in this field, we're working closely with. We brought together a great number of people back in November of 2023, and have really been focused in on how to get the community motivated around this. That's in Europe, but I should say we also have very strong collaboration in the US as well. I mentioned already that the leading number of researchers are actually coming from the US. So this is a picture from the Inertial Fusion for Energy, the IFE STARS meeting this last May in Colorado. So we're working closely with LaserNet US and Department of Energy. We're also working together with DARPA on certain projects, and in all of these universities and labs just count among our partners where we have, in many cases, very specific research projects ongoing. If I come back to what kind of opportunities are specifically available at Eli, and again, that's for the academic community, the industrial community, combination of the two. Really, we're thinking a lot about access to the high peak power lasers, so the ones that are operating in the petawatt class. So the Happels laser, which I'll show you in a moment, as well as the what we call the L4 laser, which is a kilojoule class laser. We also have a relatively high repetition rate, so 10 hertz. For those of you who've not done an experiment already, at a petawatt and 2 to 3 hertz, that there's a lot of data that could be collected, and we're talking about experiments now that are in thousands of shots rather than several shots. When we get to the higher range of the 10 petawatt class, I think we're still looking at being able to shoot several times an hour. So the amount of data is much greater. That allows for real statistical research, I think. Obviously, we're studying extreme states of matter. It's called the extreme light infrastructure. We work a lot with plasma laser interaction and with ultra high intensities. There's quite a number of secondary sources I mentioned already: X-ray sources, gamma ray sources, a lot of acceleration, everything from electrons to ion acceleration using gas jet, liquid jets, hard targets, just really whatever you could think about. I think you can probably find some example of it, Eli, today. If I go to some concrete examples, so many of these kind of diode class lasers that we talk about maybe are the next generation of lasers that are necessary. NIF is using a technology, flash lamp, that's already in the previous century, but already, very, very successful in terms of its operation. This laser, the Happles laser, was developed together with Lawrence Livermore Laboratory, and it was one of the prototypes, I would say, for the next generation of laser. And it's not there yet. This is not a laser that will actually drive a laser fusion power plant. But this is the technology. This is the roadmap that we need to go through in order to get there. This is a diode pumped laser. It'll be operating, as I said, at a very high average power, or at the 10 hertz range that we need it to be at. But I would just caution everybody that we're operating now at 3.3 hertz. We've delivered already 20 weeks of experiments on this laser last year. Getting to 10 hertz from 3 hertz is a big step. And if we're not really even operating these lasers in that range of repetition rate yet, you can imagine that's still a long way to go before we're able to get to where we need to be for laser fusion. The other very interesting laser in this class is the Aton laser. It's a 10 petawatt, 10 hertz laser. Or sorry, it's not a 10 hertz laser. It's a 1 shot per minute laser. Can operate at a higher repetition rate at lower energies. But I think this is interesting. Obviously, in this field, this is the most energetic laser that you'll be able to find as a user. We do imagine, and we are commissioning the laser right now to go to the full 10 petawatts, the full 1,500 joules by early next year. And I expect it will be in the user program by the middle of next year. And this is something that together developed with National Energetics and EXPLA, I think already we're able to offer a number of weeks of beam time. Just a few more slides and I'll be done. We can go into a discussion. Interesting also is the P3 platform for physics. This is our high energy density laser plasma physics chamber, which we already have done quite a number of experiments in there. But really what's interesting is both of those systems that I just showed you can be combined together in a single chamber to create a full range of experiments. It's just hard to go into all the possibilities, but this is definitely an area, and this is definitely one of our most, I would say, requested areas for research, particularly in this field, working together, as you can see already, with companies as well as with labs and academics and industry. In some of the areas where we are looking to collaborate with industry and also have our own capacity. So when you get into higher repetition rate, high power lasers, you think about targets in a very different way. You're using not, a handful of targets per a set of experiments, but literally could be hundreds of targets, could be more than that. And some of these targets are not cheap, and they're hard to get them already in supply if you're going to do a range of experiments. So we're already developing in-house and together with industry the capacity to be able to have targets available for users when they do come to use the facility. This is something where we started working with General Atomics on a tape foam-driven laser, but we're also developing an in-house laboratory so that we can develop more specialized targets for whatever experiment you can come up with. I think another area that was mentioned earlier by Optima and our colleagues in Lithuania, who we work closely with in many different areas, is advanced coatings and laser-induced damage thresholds. We've just put in place a large lab in a large chamber system called the Elias system. That was done together with Vacuum Innovations and colleagues from Rochester to develop the system. It's a very large system. It can handle very large optical elements up to over a meter. And we're very proud of this system, but in addition to just being proud of it, I think we're very much looking forward to using it This is something where the supply chain is very constrained. And even though we do very much work closely with PGL and also with Lawrence Livermore to develop large-scale optics, we believe there still is room for additional capacity and sometimes optimization. So generally speaking, I think Eli is absolutely within our mission, very much open to collaborating with the industry. It was also mentioned earlier, and I can't emphasize that enough, how important it is that we get more people into this field. At Eli, we have on average every year 50 PhDs working with us. PhDs may stay with us for anywhere from 6 months up to 2 years employed at Eli. So we're always looking for people with those kind of skills and who would like to be able to be at the facility, get trained, but also use it for their own work. And then we're also looking to train and put operators not only through Eli, but into the market. And we're very happy to work together with the industry on programs to give people access to one of the leading facilities in the world to train on. So I think that is all I have for now. The website's pretty straightforward, eli-laser.eu. And the bottom one is the user portal.eli-laser.eu. That's where you can see the latest call, which will be published tomorrow. I think that's it for me. Thank you.
Thank you very much for a great presentation, Alan. We have had a preview for the call that it will be published tomorrow. And of course, there are a lot of opportunities for the people in the world. I would like to ask you, what would be, in your opinion, what would be the main challenge that we should all be working together to solve for the next energy fusion projects?
I mean, well, you can go through the list, right? Everybody can here knows what they are. I mean, it was mentioned already. Laser efficiency is one of the areas where we're going to be focused. I mean, because that's very, relevant, obviously, in this field. But it's I think it's generally something that everybody agrees. We need to be able to have reliable, efficient, large-scale systems to get to the next level. We have now petawatt class lasers. They are operating, but as I mentioned earlier, it still is a challenge to operate them on a regular, daily basis and to deliver weeks and weeks of service. So I think having reliable, large-scale, powerful systems is still a challenge, and a lot of space there open for collaboration. We're very, very open for that. And I think the targets are going to be something that probably is outside the scope of what we just do at Eli. But I think having those kind of affordable targets over the long term is going to be something that needs to be looked at closely and studied very closely.
To continue the discussion, Alan, please stay with us because there is a company that has been interacting with Eli a lot and we wanted to follow your speech. We're going now to beautiful Prague to meet our colleagues from Highlights. Thank you very much for being with us today. Tell us what you can do in this field, and most important, tell us how others can help you do it better and faster.
Yeah, just a moment to share my screen. You should see this.
Yes.
Okay, so I'm coming across the street of one of Eli's, Alan just mentioned.
I know Simon very well, exactly.
we are across the street, and we do collaborate, of course, closely for more than a decade. So I will give you briefly what we can offer and how we can help in this exciting discipline. So we do laser development. That's our main core business. We are R&D institutions under the Institute of Physics of the Czech Academy of Sciences. And one of two major platforms developed at Highlights, it's a B-boy laser. And you can see here, I in purpose put these records we have achieved 3 and 2 years ago. So we have a laser in-house giving. It gave the test was we wanted to see how far we can go, 145 joule in infrared, and then in second and third harmonic 95 joule and 55 joule, and we talk 10 nanosecond 10 hertz laser. So when we were developing this laser, there was a need to have a better LIDT testing. So actually we can see how the optics that we were implementing in our laser, how it does behave, because not always you have a result as in specification because of specific laser conditions. So then we developed our LIDT lab, and we like to say here that size matters. So what we can offer here, actually testing of the optics with a large beam, and you can see the parameters that we can provide. So this is something that can be interesting for anyone who is developing a laser for such application. And then I will come to ILT presentation from the very beginning, using the modeling and numerical modeling in the laser development, which we do for more than a decade. We have developed our own models. So you have in these energies, in such energies, you have problem with depolarization, and you need to compensate it somehow. So if you don't do nothing, if you do nothing, sorry, you have losses up to 50%, and then some common compensation goes. It will be around 30. So what we have done with the proper numerical optimization and experimental characterization, of course, we decreased this significantly, and we got it around 3%. These are the things where we can jump in this from the design of the laser itself, and then we have LIDT in-house, so we can help with testing the optics. And this kind of modeling for such lasers in this class, we are quite successful in this, I would say, and we are more than happy to collaborate in this. That will be all. I think it wasn't more than 1 minute.
It was perfect. It was perfect, and I have been receiving fantastic feedback from not only from the laser technology, from the LIT lab, and the way you characterize laser-induced damage threshold, and being able to provide system integrators comparison of the different optics from all around the world. So you have been proven to be an excellent partner. There are still one topic that we haven't addressed yet, which is the metrology and especially the wavefront sensors. We have two companies in the room that I wanted them to get a saying on this supply chain. We were talking, of course, about physics and first light imaging. Let's go to physics first. Joan Oriol, thank you very much for joining. Joan Priol, tell us what you do, what you can do for others, and how we can all work together better.
Hey, can you hear me well, and can you see my screen?
Loud and clear.
Okay, so as mentioned in this meeting, there's a lot of things that needs to line up and get together and scale in order to get this fusion a reality. And I'll try in this minute to tell you what physics can do to help. Is the sound okay? Because I hear the back.
It's okay now. We solved it.
So the first things we do at physics, we can provide laser testing and focal spot optimization with adaptive optics. So we develop wavefront sensors that are available from 190 nanometer all the way to 14 microns. So first, we will measure the wavefront of the laser system. And then from this measurement, we will control a deformable mirror in order to optimize the focal spot. So for this ultra-intense, ultra-large laser facilities that are going to be needed for fusion, for the deformable mirror, we need top-class LIDT coatings and also very large scale. So we partner with deformable manufacturers, and now the state of the art would be around 800 millimeter diameter. So we need to have the wavefront sensor to talk to the deformable mirror. So for that, we have control software that allows to close the adaptive optic loops. Ultimately, what we want is a corrected wavefront, which means an optimized focal spot, which means the highest intensity on target. The second application we can help with at physics is optics testing and optical alignment. So there's like on those laser chains that are going to be required for laser fusion, so there's going to be like thousands of optics. All of these optics needs to be tested. What we offer at physics is like test station that allows to do transmitted wavefront error and also surface measurement. And we can do those wavefront testing at the test wavelength that the laser is going to be used for, that those optics are going to be used for. So some examples could be like 248, 351, 810, or on 1 micron. Once we have a live wavefront measurement, we can also use this measurement to align those optics together in order to minimize the aberration of the full laser chain. The last application we can help with is plasma metrology. So the phase of the wavefront we measure can be directly linked to the electron density of a plasma. So by pump probe experiment, we can help support laser interaction plasma understanding and support the research that's going to help create the future fusion systems. So that's those 3 applications that physics can help with. We're already in a lot of these ultra-fast, ultra-intense laser facilities, and we are looking forward to continue helping all the community in that direction.
Thank you so much, Joan, for being with us. Stay with us. Let's go now to first light imaging and hear about the wavefront sensors. Then we'll have a little bit of a discussion. Hugo Doyle, are you with us?
Hello.
Yes.
Sorry, I think we're maybe it's we're not really related
no.
to metrology, but we're a company called First Light Fusion. So maybe it's a good idea for me to introduce ourselves.
Yeah, please go ahead.
So we are a. Can you see my slides? Okay, sorry.
Yes, we do. Yes.
Perfect.
Sorry.
Thank you. So we're a 13-year-old company based in the UK. We're a private inertial fusion company. We're 100 people, so like SME level. I guess we're more of an integrator and end user, although we do also do some services as well. Our biggest focus is on target design and simulation. So we have a 25-person simulation and target design team. And the focus for the company is very much on this target on the right here. And the idea is if we can design a smarter target, and we have a phrase, a label we use for this, which integrates something we call amplifier technology, maybe it unlocks using a cheaper driver. We look at integrating with several different types of drivers, lasers obviously being a key one, and maybe you can use longer pulse lengths, which, although they might require more energy, might end up being cheaper lasers. And this is obviously vital for an economic power plant. We also look, we often forget in inertial fusion that there are other types of drivers than lasers. Obviously, this being Optica, we focus on lasers. So, Sandia, New Mexico, they're coining the maglev term, which is a hybrid scheme with a pulse power cylindrical convergent system and a large laser preheat. And there's other schemes such as ion drive, projectile fusion, and others. So I run the experimental physics team here. It's great to have simulations, and we've got two big rad hydro codes for doing target design. Without experimental validation, they're kind of useless. I'm an experimental person, so of course I'll say that. In our lab in Oxford, we have two drivers. We have a projectile driver, which is the largest gas gun in the UK, and we have a large pulse power machine, which could also drive projectiles up to about 15 kilometers per second. We can also do these cylindrical convergent loads and other geometries. This allows us to access, beyond the terapascal regime, which are the energy regimes of interest as you get to fusion and you get to the weird physics. Perhaps maybe the bit of most interest to Optica, which I don't think has been discussed too much so far, has been the diagnostics. It's great to do these experiments to benchmark the simulations, but of course you need to diagnose the plasma, and Eli spoke a little bit about this. And typically, unlike for magnetic confinement fusion, for inertial confinement fusion, you're looking at ultra fast, very small scales, and quite often in very dense plasma or materials. We're typically the end users for these ultra fast cameras from companies like Sidor, Hamamatsu, Shimatsu, and Specialized Imaging. Obviously, that needs CW and pulse laser illumination. And to have all this in our lab, so we're privately funded. So to date, we've had 77 million pounds of investments. We're not buying, 100 million pound lasers here for our diagnostics. So we need to sort of be efficient with our investments into our diagnostics. So we know the kind of systems we use for velocimetry, for measuring the shocks you get in inertial fusion. So this is VISAR and PDV systems, which Alan also mentioned. We do a lot of spectroscopy. Of course, as you go to these high energies, unfortunately, you're moving away from visible light spectroscopy and going to X-ray spectroscopy. And combined with emission spectroscopy, you're also having to do active X-ray probing. Now, traditionally, for the ultra-fast regime, you do this with a large laser. We can't afford that, so we're doing an X-pinch system, So you can make for, with £50,000 an X pinch, which is still short-ish pulse, but you can get to quite high energies. This allows you to do radiography in a sort of national lab scale images, and of course we have lots of neutron time of flight, but I guess we're less interested about this here. So hopefully this is an overview of what a lot of private inertial fusion companies, kind of where they are. They're doing in-house experiments. They're trying to make full use of the diagnostics. We have a PR picture here. We blow up a lot of Thor Labs and Edmund Optics kit. Let's put it that way. We go through a lot of equipment. Thank you.
Thank you very much for a great presentation. It is great to have you here as usual. We started on time. We finished almost on time, 4 minutes late. Allow me to run the closing credits, and then we can have a private bar discussion afterwards. It's been for us, for the Optica team. We worked really hard over the last year to bring together some of the key companies in Optica that are enabling laser fusion, and putting together in touch with those companies who, in our opinion, are driving the next generation decisions. If you want to get in touch with any of the participants today, all you have to do is send me an email, and we'll be more than happy to make the introductions. All of you who registered for the meeting today are getting the slides, are getting the participant list, and also getting the chat, because many of you commented what you can do for each other. Until the next time, this was Jose Pozo and the Optica team. Stay tuned. Bye-bye. All right, I asked my IT team now to disconnect the YouTube. Thank you so much for the IT team. Again, made it a fantastic experience. It went smoothly, sound, everything was perfect. So thank you very much. For those of you who have to go because you have to work, or you have to pick up the children from school, or you could not find